Now it's time to start with the live demo in order to use the SmartCtrl software to design the digital control of a three-phase two-level power factor correction rectifier. So this is the challenge. The challenge is the three-phase rectifier plays a crucial role in various applications like electric vehicles chargers, grid energy storage system, and also for UPS, for example. The design of control loop on digital platform represent a great channel for control engineers in additional parameters such as ADC gains and also the digital delay, and you have to take into account at the moment when you are designing the control loops. So the solution in SmartCtrl, we have implemented the two-level three-phase PFC rectifier, and the SmartCtrl allows the design and implementation of the digital control loop considering all the sampling techniques and different digital filters. I want to show you a little bit later these features from SmartCtrl. The SmartCtrl internally considers the transport line plant. So we start with a SmartCtrl software. In that case, we define all the input parameters, the input voltage, the inductance, etc. And we want to tune the PI compensator of the inner loop. The control loop will be implemented in a DQ control. And we want to tune the PI for the D and Q axis current. And then we have to tune the PI compensator of the output voltage. After that, we export this design to third-party simulator. In that case, we are using PSIM in order to verify the transient response of the control. So this is the general aspect. This is the two-level three-phase two-level PFC rectifier. We are considering just a main filter like just inductance. We have to sensing 6 parameters: the three-phase grid voltage, and also the three-phase current, and the output voltage of the converter. As you can see here, this is the FPGA. Inside the FPGA, we have the ADC converter for each of the magnitudes, and then we have to implement the control in a DQ frame. After that, we are generating the gating signal, and these signals we are driving to the MOSFETs. So in the digital control, the gains of the sensing stage and the ADC, you have to take into account when we are designing the control loops, and also you have to consider the digital delay because this is cause a phase drop in the phase of the converter plant. So in the sensing structure, the operating point of the phase current, the peak value is around 62 amperes, and also we have an analog sensing. We are considering some gain and offset voltage in order to get a sensing value within the ADC span. So the ADC span in that case is from 0 volts to 3.3 volts. This is a typical value. And also we are considering 12 bits. So as you can see, for example, if the peak value is equal to 62 amperes, the sensing current will be equal to 2.12 volts. And also, for example, if you have a minus 62 amperes, the sensing current will be equal to 0.88 volts. So these values is inside the ADC span. After that, we are considering a unity feedback. So we want to compensate all the static gain. So in order that this value, digital current, will be equal to the actual values. That means that the range of this current will be the same as the phase current of the real converter. So in the case of the output voltage is equal to 800 volts. Also, we also contemplate a gain in order that we have voltage sensing within the ADC span again, and also we have to contemplate. We are assuming the unit feedback gain, so we compensate the static gain in order that the digital voltage will be equal to 800 volts. And in the same case for the grid voltage. So the grid voltage, we have an analog sensing chain. Also, we have some value within the ADC span, and then we have to compensate in order to to achieve the unity feedback gain. So this is the control structure. This is the DQ control for the three-phase two-level PFC rectifier. In that case, we have two double loops. The inner loops control or regulates the D-axis current. We have one for the D-axis current and one PI for the Q-axis current. And for the outer loop, we have one PI that regulates the output voltage of the converter. So this PI imposed the D current reference. And also in the inner loops, we are considering the axis decoupling due to the DQ model. And we are compensating the modulator gain, as you can see here. We have the inverse part transform, and also here we have the modulating signal. So the theta angle is estimated using the phase looked loop or PLL. So I want to show you a little bit what is the structure that we are considering here. So after that, we can start. I open the SmartCtrl software. If you go to File, you can go to the initial dialog. Let's move to this window, to the screen. Okay, now this is the predefined topology. You have to go to the three-phase PFC converters. Click on this icon. Now you can see here, this is the single light diagram window. The first step that we have to do is we have to select one of the topology. In that case, you can find the two-level boost rectifier and also the Vienna rectifier. And Vienna rectifier. Then you can select different type of PLL, the phase looked loop. This is the synchronous reference frame phase looked loop. And also the second option is related if, for example, if you want to detect the sequence of the grid voltage. So in that case, I select the first option. Also, you can select different type of structure of the EMI filter. In the three-phase rectifier, it's very common to use an EMI filter in order to attenuate the differential mode and common mode current. In that case, I don't take into account the EMI filter. Also, for the main filter, you have different options. The simple inductance, the LCL filter, for example. Also, you can consider an LCL filter with active damping. In the active damping, we are sensing the current through the capacitors, and this is injected in a perturbation in the control structure. And finally, for example, you can find the LCL filter with a passive damping. This passive damping consider a resistor and capacitor that is in parallel with the main filter capacitor, as you can see here. So in this example, I select the L filter. Also for the modulator, we have a different type. Sorry, you can find different type of modulators. The typical PWM, the space vector PWM, and some discontinuous PWM. In that case, I select the space vector. And for the control, you can find also different type of control structure. The alpha beta, for example, with a simple PI compensator for the inner loop in order to regulate the inductance currents. And also you can find the alpha beta domain plus the proportional resonant current compensator. So the proportional resonant current compensator is just applied for the inner loop. And also you can find the DQ control with a simple PI compensator. So just I select this option, Then you can select different type of load, for example, a simple resistor, a constant power load, or also a current constant. In that case, I select the resistor, a simple resistor. And finally, if you select this option, you can now you can design the control loops in a digital domain. So after that, we can close this window. And now, if you click to this option, this is the control structure. You can see the control structure that you are implementing. This is the as mentioned, I showed you before, the double loop, the coupling axis, the modulator gain compensation, etc. Also, in this icon, this is the power stage. Here you can define all the electrical parameters. In that case, for example, you can define the grid voltage, the frequency in line, and the output voltage. So I want to change the capacitance to 100 micros, and also I want to increase a little bit the parasitic resistor of the capacitors. The switching frequency will be equal to 50 kilohertz, and that's all. Click on OK. Now it's time to close the power stage. Now, if you go to this icon, you can open the window related to the phase looked loop, as you can see here. This is the synchronous reference frame. We have a PI and also an integrator, the VCO, in order to estimate the theta angle. The theta angle is the phase of the grid voltage. So in that case, you can align with different axes. For example, if you select the align to the axis of the grid voltage, that means that the Q axis grid voltage will be equal to 0. So in other words, we are controlling the active power with the D current. And if you select the Q align with the Q axis, in that case, the D axis grid voltage will be equal to 0, and the active power will be controlled with the Q current axis. So in that case, I select ED. Also here, you can change the sampling frequency. In that case, we are assuming that we want to take 2 samples per switching frequency. So in that case, we have to define 100 kilohertz. Click on OK. And also, if you go to this option, this is the solution map for the phase looked loop. And if you go to this icon, this is the transfer function graphics tool. And here you can plot, for example, the open loop transfer function of the PLL, as you can see here. And if you move the cursor through the solution maps, you can see here how the body plots are updated automatically. So you can define also the phase margin and crossover frequency manually. Also, you can set here, for example, 50 degrees for first margin, and also 100 hertz. Click on OK. As you can see, all the information is updated. And then you can also change, for example, the stabilization time or damping ratio. Also, you can define here a value. Click on OK, and it's updated. Also, you can directly define with the key P and TI parameter of the PI compensator. In that case, this is the parameters in an analog way, but internally, SmartCtrl use this information in order to discretize the compensator using the backward Euler. So this is the value of the different equation in that case. As you can see here, the transfer function is implemented in a discrete domain. And this is the equivalent value of the key P and TI parameters. This is the corresponding value in a discrete domain using the backward Euler. And the last thing, you can define directly the value of the the proportional part, and also the zero of the discrete domain transfer function. In that case, I select the first margin, and also I select 50 degrees of phase margin and 150 hertz of the crossover frequency. Click on OK. And after that, I want to close this window, close the solution maps and the transfer function graphic tool. And now it's time to define the current sensor stage. So in that case, we have to define this part, define the gain of the current sensor. For example, as I showed you before, we are contemplating these values, 10 millis and offset equal to 1.5 volts. So here we can define 10 millis, and this is the bandwidth of the current sensor. The offset voltage is equal to 1.5 volts. Click on OK. Now this is the ADC parameters. So this is the minimum voltage and maximum voltage is the span of the ADC. In that case, it's from 0 to 3.3 volts. And also you can define the number of bits of the ADC. Finally, I use the unity feedback gain in order to compensate this option. So, SmartCtrl internally compensate all the gain in order that we are considered unity feedback gain in the sensing stage. So another thing that is important in digital control is define the sample technique and the modulating technique. In the sample technique, you can find two options: the synchronized sampling and oversampling. And also for the modulating technique, you have two options: the single update and double update. And if you selected the oversampling technique, also you can find here a multi-sampling update. So in this example, I select the synchronized sampling and also the double update option. That means, so this is the sampling strategy, sampling technique that we are assume in this first example, that we are selected the synchronized sampling with a double update. That means that we are taking the current sampling in the vertices of the modulating signal, as you can see here. So we are taking two samples of the current inductance currents per switching frequency. As you can see here, this is the first sample, the second sample, and again, the first, second, and so on. So another thing, in the output voltage sensing, also we are contemplating a synchronized sampling that assume that we are taking both samples are taken at the same time. That means that we are taking at the vertices of the carrier signal, we are taking the inductance current sample and also the output voltage sample here. Also, we are assumed that we have enough time in the half of the switching period. Also, we are assumed that we have enough time to make the ADC conversion and also the calculation of the DQ control. So in this calculation time, we are considering that we have enough time to operate the two PIs, the equation editor of the equation difference equation of the outer loop and the inner loop. So after that, we have the modulating signal, and we updated this value the next sampling frequency or sampling period, as you can see here. So this signal is updated in the next sampling sampling frequencies. So in that case, the digital delay, we are formed with two parts. The first part is fixed, is related to the calculation time. This is a half of switching frequency. And also we have another part that is related to the DPWM, the digital PWM, as you can see here. So this part is also fixed, and for the double update, SmartCtrl consider this value. So you don't have to do anything because SmartCtrl already internally considers the corresponding digital delay. So this is just for information what means the synchronized sampling with a double update. So for the others combination, if you go to help, you can see here what is the difference combination. For example, if you select the synchronized sampling and single update, that means that we are taking one sampling of the one sample for every switching period, as you can see. And if you select single update, the modulating signal is updated in the next sampling period, as you can see. This is the synchronized sampling with a double update. We are taking every 2 times per switching frequency. And also the modulating signal is updated in the next sampling frequency, as you can see here. We are taking the sample here, and the modulating signal is updated at this point. If you selected, for example, oversample and single update, that means, for example, if you select the NS equal to 4, that means that we are taking 4 samples every switching frequency. So that means that we are taking 4 samples. 1, 2, 3, 4, and again. And after the last sample, we are updating the sampling, the modulating signal in the next switching sampling. That means the oversample with a single update. And also, if you selected the oversample with a double update, that means that in the second sample, you are updated the modulating signal here, as you can see here. And if you selected the oversample and multi-sampling update, you can take the sample and then immediately update the modulating signal, as you can see here. So in our case, I selected the synchronized sampling, double update, and that's all. Click on OK. Now it's time to define the gain of the grid voltage. In that case, I select a gain of equal to 0.004. Click on OK. The span of the ADC is the same. The bits number is 12, and unity feedback gain. Click on OK. And now it's time to select the output voltage sensor. So here again, we have to define the gain of the voltage sensor. It's equal to 3 millis. The bandwidth of the voltage sensor, also the span of the ADC, and here again you can select the synchronized sample. This is the option that I show you here. This is why we are taking both samples at the same time, as you can see here. And also you have to select the unity feedback gain. Sorry, 3 millis. Click on OK. And after that, it's time to define the resolution of the carrier signal. In that case, for example, if you consider 10 bits for the resolution of the DWDM is equal to 1024 steps in that case. So click on OK. This is the space vector modulation. Then you can close this window, and now it's time to open the inductor current compensator and also the output voltage compensator here. If you go to this option, you can open the solution map for the inner loop and also the solution map for the outer loop here. And finally, again, we have to open the transfer function graphics tools. So in that case, I will disable the frequency response of the PLL, and I want to enable the frequency response of the open loop transfer function of the current, and also for the output voltage here. Again, here, if you move the cursor through the solution maps, all the things are updated automatically. Also, in the inductor current compensator and output voltage compensator, you can set the phase margin and crossover frequency manually, and also you can, for example, define directly the Kp and Ti, and also the proportional part and the zero part of the equation, the different equation of the compensator. Remember that this compensator will be implemented in a discrete domain. So in that case, for example, I select 50 degrees of phase margin and crossover frequency equal to 4 kilohertz. And then click on OK. And for the outer loop, I will set a 40 degrees for the phase margin and 8800 hertz for the crossover frequency. Click on OK. So as you can see here in the crossover frequency, this part is provoked for the digital delay. So as mentioned before, the SmartCtrl already considered the corresponding digital delay. As you can see here, this is the phase drop that is provoked due to this digital delay. So if you go to the schematic option icon here, this is a summary. All the combination that you selected for the power stage, the control structure, the PLL, and also for the sensing stage and the modulator. So this is like a summary in order to get a general overview of the control structure, etc. So now it's time to export to PSIM. If you go to, sorry, okay. If you go to this icon, you can select the PSIM option, go to schematics. Now I set a name. In that case, I set example number 1, click on open. And now SmartCtrl will create a PSIM template for you. So now we have to wait some seconds. Okay, we got it. So as you can see here, we have the three-phase PFC. This is the power stage. In the parameter file, you can find all the parameters that we define in the SmartCtrl, the gains of the sensor, etc. Also, for the current stage, for the sensing stage, we are in this PSIM simulation, we are not implementing the offset voltage because the offset voltage does not affect the dynamic of the system. But if you want to check if the ADC, if the sensing voltage of the current is within this ADC span, we can add the offset here. For example, I select in this, I define 1.5 volts. Here, and also I want to apply to the other phase. So after that, we have to compensate this offset voltage. In that case, we have to subtract the offset voltage is equal this divided by the gain of the sensor. As you can see here. In that case, I put a voltage proof here that it's called the current digital. So we have to copy this part to here and here. Okay, and also I want to add another proof here that it's called current sensing. For example, this is the output voltage. In that case, we are not considering a offset voltage. Another voltage proof, I want to measure the modulating signal, for example. The modulating signal. And also we want to measure, for example, the theta angle. The theta angle. And the last thing, I want to put an limiter here in order to limit the current reference. Remember that the peak value of the current reference, it's in the operating point is 62 amperes. So in that case, for example, I define from minus 100 amperes to 100 amperes. As you can see here, sorry, it's not here. Mistake. The limiter is applied here because the outer loop imposed the reference of the inner loop. So in that case, as you can see here, all the transfer function of the PI compensator is implemented in a discrete domain. We are considering the zero order Hall in order to represent the ADC function, and also we are considering the gain of the ADC. In this block, we are compensated the gain of the ADC and the sensing stage. And now it's time to run the simulation. I increase a little bit the total time. And also I want to add, for example, to measure the D current, and also to measure the reference. So now it's time to run the simulation. We have to wait some seconds. Okay. Let me open the scene view. So here you can see this is the output voltage. Achieve the reference 800 volts. Also, sorry, I want to add one more voltage proof. At this point, there is whole digital voltage. So now it's time to run the simulation again. So, for example, digital output voltage. So this is the digital output voltage, and also we want to see the three-phase current. As you can see, it's close to the 62 amperes. And also, for example, you can see the modulating signal. This is the modulating signal, or for example, we can compare the reference of the D-axis current with the current axis sensed. As you can see, all this is stable. And finally, for example, you can check the theta angle. This is the theta angle of the PLL. So one thing that is important here is that if you can make a zoom in this part, we have some the ripple of the output voltage is very large. So the main problem here is that we are taking the sampling in the same instant as the current. So in that case, the digital voltage is changing every sampling frequency, as you can see here, and not correspond to the average value of the output voltage. So this is the problem with this stability control. So as you can see, this information is related to the phase current. You can see a little bit distortion in the current. So in order to improve this part, we are selecting a second example. In that case, we are going to the output voltage sensing, and we want to select the oversampling technique. In the oversampling technique, I select, remember, this is the number of samples that we want to take into account every switching period. So in that case, we are taking 4 samples. And also I select the option for the digital filter. In the digital filter, you can find different type of filters. For example, you can select the low pass filter, the first order low pass filter, a second order low pass filter, and also you can use the moving average filter. In that case, I select the moving average filter. So, and click on OK. So that means this is a second strategy. So that means that in the voltage sensing, we are taking 4 samples every switching period. So a moving average filters, the average is calculated for each sample. This is the expression of the moving average filter. So we are taking, that means that we are taking a sample of the output voltage, and then we assume that we have enough time to make the ADC conversion and also the moving average. This is a very simple expression. And after in between the samplings. So after that, if you remember, for the inner loop we selected the double update and synchronized current. So the current is sampling every 2 times per switching period at the vertex of the current signal. And for the output voltage, we are taking 4 samples for per switching frequency. So this is sample 1, 2, 3, and 4. And after the second sample, we start to operate the different equation of the PI. So at this time, we have the modulating signal, and then it's updated at the next sample period of the current. So in that case, it's assumed that there is a sufficient enough time to execute the PI compensator for both loops in this time. So the PI frequency of the PI frequency is equal to 2 times the switching frequency. That means it's equal to 100 kilohertz, and for the moving average filter is 400 kilohertz, the switching frequency. So in that case, we have to click on OK. Again, I want to close this, and now it's time to export to a PSIM simulation. I set a name, example number 2. Click on Open. We have to wait some seconds. So now, as you can see here, for the output voltage, now we have the FIR filter. This is the moving average filter. So in that case, I want to put here a voltage proof that is called digital voltage, and also for the current. Okay. Also for the current. Again, we want to add the limiter here to minus 100 ampere to 100 amperes. After that, we want to measure again the modulating signal. Here. And the last step that we have to do, so we have to copy the coefficients of the digital filter, in that case, these values, copy, and paste it here in the coefficients. So click on OK. And now it's time to increase the total time to 0.1 seconds. And finally, click in simulation time. So now I want to show you the three-phase current. As you can see here, the distortion will be, the distortion disappeared. So, and for example, if you select the output voltage, this is the output voltage measured in the power stage. This is the output voltage. And then I want to compare with the digital voltage. So in that case, as you can see here, the ripple is attenuated, and this is the average moving average filter. So as you can see, it's like the average of the output voltage. And that's it. This is the second example. And finally, for example, if you want to measure the bandwidth of your control loops, you can add a perturbation here in order to make an AC sweep. For example, here I want to add a sine voltage source. I want to change this value, this name, and set the amplitude to 0 equal to 0, for example. And then I have to add the AC sweep proof. Others proof, AC sweep proof loops. I can put here. And the last thing is to add the configuration of the parameter sweep. No, AC sweep here. AC sweep. And here we start frequency equals to 100 to 10 kilohertz. And also we want to change a little bit the amplitude of the perturbation. So after that, we can click on run the simulation. This simulation takes some minutes. And that's it. With this frequency response, we want to check if the bandwidth of your control loops is equal to 800 degrees and 800 hertz, and also the phase margin equal to 40 degrees. So we want to wait a little bit. In that case, we are not in this simulation. We are not implementing the voltage, the offset of the current, because I mentioned before, the offset doesn't affect the dynamic of your system. So we have to wait some seconds, a little bit. For the PLL also, as you can see here, we are implemented the integrator with this is based in backward Euler, and also we have a PI in discrete domain. Also, we are sampling here the grid voltage, and that's it. We have here the coupling axis, and this is the compensation of the modulating gain. As you can see here, the 0 dBs at the magnitude is very close to 800 hertz, and also the phase margin is equal to 40 degrees. I want to export this information. If I go to edit, view data point, file, save as, and I want to call this, for example, PSIM file. Save a TXT file, click on OK. And now in SmartCtrl, if you go to the transfer function graphic tools, if you right click on this section, you can select the option that it's called import. And also you can import directly the transfer function. So this is the TXT file. click on OK, and as you can see, both transfer function match. So we have a little bit difference in this frequency range, but this this phase difference is related to the time step. If I decrease the time step to 0.1 microseconds, for example, I have an backup. Let me delete this transfer function, import. So if I select this, you can see here how the phase is already matched in practically all the range. So that is all for the webinar. And also, if you have any question, please let me know right on the chat or raise your hand. And thank you for attending for this webinar.